Today in this lecture we are going to start a new topic very important for computational purpose, so called determinants. This will have several sections, and for the sake of completeness I want to first discuss about permutations, or rather I want to discuss permutation groups. Very important class of groups when one wants to study finite group theory, and we have to use these permutations, especially some invariants attached to permutations in the theory of determinants. That is the reason I want to do this topic more thoroughly. So let us introduce a notation in the beginning. For a set X, let us denote Sx all bijective maps from X to X. Sigma is bijective. Note that if sigma is bijective, then sigma inverse exists, and sigma inverse is also bijective. Sigma inverse is the inverse map of sigma. Therefore, this set Sx is closed under inverses. Also, it has a natural binary operation of composition of maps. This of maps is a binary operation on Sx, and as we have seen several times, that composition is such a natural operation that it is associative. It has an identity element, namely the identity of the identity map of X. This is the map X to X, which map X to every X to itself. So therefore, this Sx under composition is a group. This group is called permutation group of X. Group 1X. Also, it is called a symmetric group 1X. And we will be mainly interested in when X is a finite set, namely, in fact, we will, in the theory of determinants, we will use this for X equal to n star n, which is the set 1 to n. And note, in the case of finite set X, to check sigma is bijective, you either have to check sigma is injective or surjective. One of the checking is enough because of the pigeonhole principle. Once it is injective, it will be bijective, map from same set to set. But this is only true for finite sets. If it is not finite, then there are injective maps which are not bijective and so on. But we will mainly concentrate on this. So, little word about these notations. For example, very important thing which I want to bring it to your notice, that I will simply write sigma tau for sigma composed tau, and we will apply tau first and then sigma. This is from this side, which is against our writing. Okay. So, for example, if I have a permutation when n equal to 3 and if I have a permutation, so I will write below 1 image of 1, that is sigma 1, this is sigma 2, this is sigma 3. This is a permutation sigma. Suppose I have another one which is, I will call it tau, which is 1, 2, 3, this is tau 1, tau 2, tau 3. I want to demonstrate you how does one compose. So let us take, this is 2, 1 and 3. So note that when you want to control somebody's bijective or not, you just have to look at the image row of sigma and check that all the entries there are different. So this is 1, 3, 2. That means under sigma 1 goes to 2, 2 goes to 1, 3 goes to 3. Under tau 1 goes to 1, tau 2 goes to 3, 3 goes to 2. And composition then, sigma tau will be, first you write down the first row, that is 1, 2, 3, and start reading from tau. 1 goes to 1 and then look at 1 goes to 2, so 1 will go to 2 under composition. 2 goes to 3, 3 goes to 3, so 2 will go to 3. And we don't have to write, we don't have to check, but we can check 2 goes to 3 goes to 2 and 3 goes to, no, 3 goes to 2 and 2 goes to 1. So this is correct. That is how one writes the composition. Let us compute the other way also, sigma tau, tau sigma. So again 1, 2, 3. So where do 1 go? First we have to apply sigma now. 1 goes to 2, 2 goes to 3, so 1 goes to 3. 2 goes to 1, 1 goes to 1, so 2 goes to 1. 3 goes to 3, 3 goes to 2, so this is 2. And note that these two permutations are different, because image of 1 is 2, image of 1 is 3 here. So it's obvious that sigma tau is not tau sigma. So from this it is clear that the group Sn is not commutative if n is at least 3. So it's not commutative group. So one has to be little careful with the groups, because they are not abelian in general. Another thing which I will note, but I will not prove it, which is very well known. So but I would have written the proof in the notes. So let me write as a proposition. Cardinality of Sn, the group Sn, is n factorial. Proof, I will just say that by induction. I will not do the proof today, but okay. So the most important consequence of this permutation group or definition is the theorem of Cayley. That says the following: let G be a group, G be any group for any A in G. Let lambda A denote the multiplication on left by A. That means any element x in G goes to Ax. This is not a group homomorphism, but it is definitely a bijective map. Then lambda A is actually bijective. And so that means this lambda A actually is an element of S of G, permutations on G. And then think of this lambda as a map from G to S of G. So this is a group under composition and this is a given group. So this map A goes to lambda A is an injective group homomorphism. So this is very important because suppose for moment G were a finite group, that means we have given a isomorphism of G onto its image in the permutation group. So if one want to study anything about group, finite group, we might as well study the permutation groups and all information about permutation groups, what are the subgroups, what are the orders of elements and so on. So the finite group theory will therefore get reduced to study permutation groups. So now let us prove this. This is very easy to prove. Proof. First of all, I have to prove that lambda A is bijective. But note, if I take lambda A composed with lambda B, this is nothing but lambda suffix AB. This is obvious because to check this equality, I just have to evaluate on arbitrary element of X. Both are maps from G to G. So if I take any X in G and evaluate both the sides, this is lambda AB on X, which is ABX, left multiplication by AB, and this one is first lambda A of lambda B of X, but this is first inside thing, so that is lambda A of Bx, and this is ABX. But you see it's a associative property of the group operation G, therefore these two maps are equal. Therefore we have checked that this composition of lambda A and lambda B is lambda suffix AB. So in particular, if I given any A in G, we know that A inverse exists in G because it's a group. So lambda A compose lambda A inverse, this is nothing but lambda A inverse, which is lambda E, but lambda E is clearly identity map of G because E times X is X for every X. So therefore this lambda suffix A inverse is nothing but lambda A inverse of the lambda A map. So that shows in particular that this lambda A map is a permutation. Now we have to check it's a group homomorphism. To check it is a group homomorphism, so we have this lambda of A equal to lambda suffix A. So we have to check that lambda AB is same thing as lambda A compose lambda B. But this is what I have checked earlier. So that means it's a group homomorphism. This is a group homomorphism. Now I want to check it is injective. So to check the map group homomorphism from a group, one group to the other group, to check it is injective, we only have to check that kernel of that map is trivial. We have to check this. That means if lambda A, which is lambda suffix A, if this is identity map of G, then from here I want to conclude that A is nothing but the identity element. But that is, this is equality. So for every X it is equal. So that means lambda A X equal to X for every X in G. But this is by definition AX. This is true for every X. So I can cancel X. So I conclude A equal to identity. Cancellation is allowed because we are in a group. So that shows that this Cayley map, this lambda is also called Cayley homomorphism. Cayley was an English group theorist, very important. The same Cayley Hamilton theorem, the same Cayley. Okay. Now the next one I want to check actually that the the center of this group is, so this is the lemma. This lemma is not used in the determinant, but those who want to do group theory, finite group theory especially, it will be very important for them. So let X be any set with at least 3 elements. Cardinality X is at least 3. It may not be finite, but it should have at least 3 elements. Then the center of the group Sx is, what is the center by definition? Center by definition is all those permutations which commute with every other permutation. Sigma tau equal to tau sigma for all tau in Sx. So this is called the center of Sx. It is clearly a subgroup. Because if sigma is there, sigma commutes with every tau. So if you multiply this equation from this side by sigma inverse and that side by sigma, sigma inverse will also commute and so on. So it's a subgroup. And the center I want to prove, we want to prove that Z of Sx is the trivial group. That means the only element in the center is identity map. Identity map is obviously there, so this inclusion is obvious. Now I will prove it to you that if any other permutation belong to the center, then it must be the identity. So, or I will prove that, so proof, we will prove if sigma is in Sx and sigma is not identity, then I will find, then we will find a permutation tau such that sigma tau and tau sigma are different. That will mean that sigma cannot belong to the center. Okay, so for that I will have to use cardinalities at least 3. So sigma is not identity. So therefore we can find there exists X in X such that sigma of X is not X, because it is not identity map. So at least at one X it will not be the same. Okay, and let me call this sigma X as Y. And I have these two elements X and Y in X, but X has at least cardinality 3, so I will choose the third one. So choose Z in X such that Z is different from X and Z is also different from Y. Then I will take tau to be, I am looking for tau. So I will take tau to be equal to a permutation which maps Y and Z interchange. So Y goes to Z and tau of Z is Y, and all other elements are fixed. All other elements in X are fixed under tau. So we get a permutation tau. And now we just simply have to check that sigma tau is not tau sigma. So let us check that. So I want to check that sigma tau is not equal to tau sigma. So let us evaluate this on X. This is equal to sigma of tau X. But X is different from Y and Z. So tau X is X. So this is sigma of X, which is Y. This is this side. Let us compute this side, that is tau sigma on X. This is tau of sigma X. but that is tau of y, but tau of y is z. So this side evaluated at x, is answer is z, this side evaluated at x, answer is y, and y is different from z. So that shows that sigma tau is not tau sigma. So we have proved that the center of a permutation group is a trivial subgroup. Okay, now the next proposition shows that this permutation group doesn't depend on the set x, it depends only on the cardinality x. So let me write the proposition. So suppose let x and x prime be two sets of the same cardinality. May be finite, may not be finite, but when one says the sets have the same cardinality, that means there exists a bijective map from one to the other. Bijective. There exists f which is bijective, and I will denote bijective map like this. That is the meaning when you say two sets have the same cardinality. Then the map kappa f. Kappa f is, I am defining a map from the permutation group Sx to the permutation group on x prime. What is this map? So I have to map permutations. Where do they go under this map? So sigma, this is a map from x to x, bijective map from x to x. And I want to map it to a bijective map from x prime to x prime. This is what I am looking for. But I know there is a f here, which is bijective. And then the inverse of f will be in the other direction, f inverse. And I have given this map, this, and I am looking for this. So what do I do? Oh, I wrote the other direction. So let me correct here. So this is from here I want to take f inverse, follow it by sigma, and then follow back by f. This is f is the other direction. So this is the map we were looking for. Let me draw it a dotted thing. This is the map we were looking. This is the map is this. So first f inverse, then sigma, then f. So this map is f inverse sigma f, which is indeed a map from x prime to x prime. This is bijective, this is bijective, also this is bijective. So composition of bijective is bijective. So therefore we indeed have a map from this Sx to Sx prime, and this is a group isomorphism. Then the map is an isomorphism of groups. So as far as the group structure is concerned, the group structure doesn't depend on the set x, it depends only on the cardinality x. So, and this is just mere checking, so I will leave it to you. Just check that it's a group homomorphism and check that it is bijective. So bijective is also clear because I can actually give the inverse map. Or let me say a few words. So first of all, kappa f is bijective. In fact, inverse of kappa f we can write directly. This is kappa suffix f inverse. And also we will have to check that kappa f of sigma tau equal to kappa f sigma times kappa f tau. This is what we have to check for every sigma tau in Sx. That will check that it is a group homomorphism. But see, this is equal to what? By definition it is F sigma tau F inverse. But composition I can rearrange the brackets. So, this is same as sigma F sigma, and I will write F inverse here and kill that by adding F here. This is identity. So, it does not make, and this one is this and this one is this. So, therefore, it respects the structure. So, it is a group homomorphism, it is bijective already. So, it is a group isomorphism. So, if you want to study this group, the permutation group on X, it is enough that we can choose a set of that cardinality, and that set X I will choose n star n, and our problem is to study finite, and in this case we will stick to the notation Sn equal to S of 1 to n, which is S of isomorphic to S of x. So, if I want to study this, I will study this. Okay. Now, I want to study what are the elements, what are their orders, how to find their inverses, and so on. So, this we will do it after the break.